In Chapter 11, we're only going to cover a couple of definitions and sections. Most of this unit has been cut out off the AP test. It's not very involved at all. We're going to do a little bit of review of lattice energy, some very simple definitions, and then some concentration calculations. So lattice energy is a review here, because we're talking about mixing solutions and intermolecular forces off of Chapter 10. And when you dissolve something that's ionic, we often look at the energy requirements. So if we know that lattice energy, if you remember, that's the energy to make a substance, then we can, it's the same amount of energy to break the substance apart so that it'll dissolve. So here's the lattice energy for this reaction. Okay. So lithium plus fluorine gas makes LiF solid. To figure out the lattice energy, we need to remember what that definition is. Lattice energy is gaseous ions coming together to make the solid LiF. Okay. This equation up here with single elements in their normal state, this is our delta H reaction. Okay, that's the total. Lattice energy is one of the pieces. So this is what you need to remember here. Here we're turning lithium solid to gas. We need that 161. The first ionization energy is lithium turning to lithium plus 1. We need that. Electron affinity for fluorine. Let's do these a little bit out of order here because we want to do the order that they happen chemically. Fluorine, we'll do the bond energy first. 2 F fluorines. We only need half of that because there's only 1 fluorine in our final product up there. And then we'll get to the electron affinity, which is fluorine turning into F minus 1, so we need that. And then the lattice energy is coming together to make the compound. All of that equals delta H. Delta H is the final. The formation is the final. So here in this problem, when they give us delta H, they're giving you the final. X, your lattice energy, is on this side of the equation. Okay, so don't forget that little tiny piece. Otherwise, we just need to manipulate these. We need to add them together. We've got the 161. We've got 520, negative 328. Now we only need 1/2 of the 154. Okay, so half of that plus X for my lattice energy equals the negative 617. So we put all of those things together. I'll let you guys double check to make sure you're getting the math right. The lattice energy comes out to be negative 1047. That is the energy released when lithium fluoride forms. So if we think about intermolecular forces and we want to dissolve the lithium fluoride, break it apart, go backwards, it would be positive 10,000 or 1047 kilojoules. And that's kind of where we're going next. Before we get there, there are a couple of things, a couple of other units that we use to talk about concentrations. Molarity is one that we've done throughout the year, and chemically this is a really common one. Mole fraction is one that we've often done with gases. We can do that with solutions as well. Chapter 11 is really about solutions. So molarity, very common. Mole fractions are very common. But those don't make sense in the real world. So if you go to the grocery store, you often see things as mass percents. when you see 3% hydrogen peroxide, you see vinegar solutions, salt solutions, liquid solutions that you buy at the grocery store, they often have percentages on them instead of molarities, because the common person walking on the street doesn't understand molarity. So there are equations for these things, but if you just think about them, it's a percentage, part to whole, mole fraction, part to whole. You already have these things. You just need to find the little pieces and parts that go in them. So let's do molarity first. Let's get this a little bit smaller. Our formaldehyde, we have 5.84 grams. And it is 30.03 grams per 1 mole. So 0.1945 moles. Sorry, my writing went off the page a little bit. We're going to do mole fractions, so we need the water as well. We have 100 grams of water. 18.02 grams per 1 mole of water. And that's going to give me, this is the H2CO, this is 5.549 moles of water. So we have the moles of both, and let's see if that's enough to get us where we need to go. The first thing here is molarity. Molarity is moles per liter, and we're talking about formaldehyde, not the water. So we have 0.1945 moles of formaldehyde, and then 104 milliliters of solution. All right, and that's given in the problem, this 104. Sometimes they give you the density, and you have to figure out what the volume is. So it wouldn't be too much of a stretch to do that as well. This will give me 1.87 molar. Oops, this should be, I'm sorry, 0.104 liters. I got that wrong. 0.104 liters, 1.87 molar. The mass percent, it is like it sounds, it is a percentage. We have 5.84 grams of formaldehyde. We have 100 grams of water, so a total of 105.84 grams total, part to whole, times 100% equals 5.52%. And yes, you have to have that 100% written down to get credit. And the last one is a mole fraction, which we just got done doing with gases, but we can do it with solutions as well. Mole fraction. So the chi, if you remember that, H2CO. We have 0.1945 moles of formaldehyde. And if we add that up with the water, we get 5.7435 moles total for a mole fraction of, this one is not times 100% because it's just a fraction, 0.0339. So molarity, mass percent, mole fraction. Don't memorize equations, memorize units. If you know what the units are, you know how to solve the problem. Moles per liter, grams over grams, moles over moles. Just think about what the units are in the problem. That is the equation. You're going to see two other terms in your book as well that I want you to totally ignore. One of them is called normality. Do not do anything with normality. The other one is molality. That is not a typo. Molality. Unfortunately, I can't just skip these problems because they're often in the same problems with the molarity, mass percents, and mole fractions. So any problems that you're doing, you do not need to know what normalities are or molalities. They're not useful for what we do, and they're not on the AP test. The last thing we have here is more of just a discussion on this chart. This chart shows the energy requirements behind the like dissolves like rule. And you kind of saw in the teacher notes here, we've got delta H1, 2, and 3. Delta H1 is, we're just going to kind of teach through this one. It's not really a sample problem, but expand the solute. And then 2 is expand the solvent. And 3 is mix. Okay, mix them together. So if you want like dissolves like, if you want two things to dissolve, first thing I want to point out is when you're expanding something, delta H1 or 2, notice these are all endothermic. You're breaking intermolecular forces here. Okay, if you have particles that are really close together, and you want to break them all apart, you need to overcome all of those forces so that you can get them spread out. The same is true for the solvent. If we have water molecules, they're all connected. If we want the salt molecules to go in between those water molecules, we need to actually spread them out a little bit. That takes energy. We don't think about this when we mix things, but there is not space in the liquid for the salt to go unless the salt actually breaks it apart a little bit. So it has to get in the gaps. They both have to break apart. And then when we mix them, energy is, of course, released. Now they are mixed up, touching one another, exothermic. Two things come together, we get a solution. So this is an explanation of the energy requirements here. If two things are polar, the energy requirements are both very large. And when they come together, it'll be very attractive to one another. So this very, very large mixing, when they come together, since they're attracted to each other, it gives me a very small heat of solution, but I can get a solution here because I have things that are polar. Even if it's a little bit positive, we can still get something to form because it's a very, very small difference between all of these terms. If I have something that's polar and nonpolar, one of them is going to have a very small energy requirement because it's nonpolar. It has very weak forces, LDF. The other one, being polar, is going to have a very large energy requirement. And there's almost no attraction when they come together. So the difference, the dominating term here, is this large positive one, which is going to result in a very large positive, not favorable energy requirement, so nothing happens. So this is the energy reason why, and this is the exact same thing, why like dissolves like, why two nonpolar things, a polar and a nonpolar thing, will not mix. There is a very large positive energy requirement that it's too hard to meet. When two nonpolar things come together, there is a very small energy requirement. And there is an attraction when they come together. So the solution threshold is so small in these two that I can get solutions to form if I have a small threshold that I need to overcome. That's really the reason behind like dissolves like. Conceptually, you don't have to memorize all of this chart, but you already know like dissolves like. This is just a reminder that there are energy requirements behind all of it, and we do kind of get this delta H1, delta H2, and delta H3 in the mix here. In your book, this is where the lattice energy comes in. To expand the solute, let's do this. To expand the solute, this is often the opposite of lattice energy if this is ionic. Because the lattice energy is coming together, we want to break it apart. So delta H1 is the lattice energy. Delta H2 and 3 are really hard to measure independent from one another because they kind of happen at the same time. So even though this is delta H2 and then the mixing is delta H3 and all of those together make the solution, we really put those together and we call them the heat of hydration, the spreading out of the water and making a mixture. This gives us a way to measure the solution and calculate it. So 2 and 3 actually go together. So you will do problems in the book where you're given a heat of hydration and a lattice energy, and you're expected to calculate the heat of solution. We don't really look at delta H1, 2, and 3. This hydration is a combination of 2 and 3, and then the lattice energy, the opposite sign of the lattice energy is delta H1. So you will do some calculations there. All right. This is like a density problem. You still know like dissolves like. You don't have to calculate those things here, but the following substances are slowly added to a beaker or graduated cylinder. CCl4 with a density of 1.4, 50 milliliters of water, 50 milliliters of cyclohexane, and you can see the densities are getting lower and lower. Would there be a solution formation? Well, if we read this problem correctly and we pour them carefully, since the CCl4 is a 1.4 density and it has LDF forces, my water is a 1.0 density and has hydrogen bonding forces. Sometimes we think they have different densities, they won't mix. That's not really true. They won't mix if they're different forces. Since these are polar and nonpolar forces, they will not mix. And then if we're careful when we add this C6H12 with a density of 0.8, it should just sit on top of the water. So based on just like dissolves like, we can get a density column here because I have nonpolar, polar, nonpolar. If any two of these next to each other were the same, they would mix. Even if their densities are different, they would mix. Okay, so we will get a density column here. We go back to the question and it says, if solid I2 flakes are added to the system, which layers, if any, would they dissolve? Well, I2 is a nonpolar substance. It's linear. We should see it dissolve in the nonpolar forces. It should not dissolve in the water, but it will dissolve in the C6H12 and the CCl2. And it might actually turn those, I believe, purple is the color of the iodine solutions. And then the very last thing we're going to touch on is just an obscure definition of a colloid. It's another type of solution. If we had a very large container and we could zoom in on the particle sizes, it's a mixture of sorts. It is actually a homogeneous solution, so it is evenly mixed, but it has some strange properties to it. One of the considerations is particle size. So if we had a water-based solution with a bunch of very, very small water particles, and hopefully you can see all the dots starting to fill in this solution. There's a lot of water in the background. A colloid is when you have something with a slightly larger particle size, and it does not actually have to dissolve. So here's, hopefully I've got enough water in the background there that you can see. And then we have a colloid with some particles that don't really dissolve, that are a little bit larger. Suspensions are another type of solution that have really large particle sizes. These aren't drastically different, but their polarities, they don't actually have to mix. They won't settle out. They don't mix, but they don't actually settle. They're just kind of there in the solution. Some of the examples your book gives, and you can just kind of read on this. If we think about milk, milk is a very traditional example of a colloid because it has lipids, it has fats that are nonpolar, and it has water in it as well. So you don't actually see those things separate out in the milk unless you leave it sit out on the counter for a very long time. It's homogenized, it is a colloid. Those fat particles do not precipitate out. They are mixed into the solution, even though they are not technically soluble in the milk. So just a new definition for colloids that you might see on the AP test. And that's all you need to focus on from Chapter 11. The rest of it is being omitted. Good luck.